It's go time. Hey everyone, happy last day of reInvent. Woo! My name's Nikki.
I'm Zelda.
And I'm Ian, and welcome to our talk on building with the new AWS SDKs for Rust, Kotlin, and Swift.
Figured we'd start with a little bit about us to, give us some credibility here. I have been a Swift developer since pretty much it launched. Also, if you don't know me, I run the AWS podcast bi-weekly with Simon and Alicia. I also do the launch shows. And this SDK is my first baby, and this one will be my second.
Yeah. As I said, I'm Zelda. I've been a Rust enthusiast since about 1.0 in 2015. I host the Chicago Rust meetup. I'm about what you'd expect for a Rust developer. This is my first reInvent, and I'm actually new to the Rust SDK team, and I'm really excited to be working in open source.
And as I said, my name's Ian. I'm a bit newer to Kotlin than these two are to their respective languages, but I've been developing in Java and Scala for a long time, so know the JVM ecosystem pretty well. And I've been a big fan of AWS SDKs since I started using them back in 2014. And so when an opportunity came along to develop a new one for Kotlin, I jumped on board.
The agenda for today. All right, so we're going to go over some SDK fun facts. Then we're going to go into some historical context on the SDKs. We're going to talk about what Smithy is in case you missed previous breakout on that or any discussion about Smithy. The new SDK architecture that we designed and built our SDKs in. Some of our shared features. We're going to deep dive into each one. And then we have a really cool demo planned where we actually used all of the SDKs to build one awesome demo for you.
All right, so first some fun facts, some kind of background information here. Currently, AWS supports 12 different SDKs, each for a different language, including the 3 that we're here to talk about today. And these SDKs are generated as opposed to maintained by hand, which means that they get the latest AWS services, latest AWS APIs and features as they come out. Every day at 11 o'clock Pacific time, we regenerate each of these SDKs, which means we regenerate all the code for them, we rebuild them, and we republish them to third-party package managers. And in that way, they all maintain a kind of a feature parity so that no matter what language you're working in, you should get new AWS features at roughly the same time.
Some historical context. So the older SDKs, meaning most likely any SDK besides our 3, well, and a couple others, was built in this way. So there was a C to J model. So C to J stands for Coral to JSON. Coral was our internal schema. Fortunately, it's not public. But it was a schema that we were using, or DSL language, whatever you want to call it. And then we had a legacy code generator that we would run the model through. And then it would spit out a client SDK. So you can think the Java SDK. And it would be on top of a library called AWS Core. So this was a runtime library. So this had networking. It had authentication, specifically for credential providers. It had the ability to handle regions and anything that you can think of. So all of the combined pieces of networking and things that you need for an SDK, like serialization, were literally integrated with AWS-specific things.
Yeah, so now we have a thing called Smithy. Smithy is a kind of a public version of C2J with some added improvements. Basically, you would define a model for your service, and then you'd be able to code generate it. Next one. So the architecture of this looks very much the same as that old architecture, except with some key differences. So here we have a Smithy model. We run it through CodeGen, and that gives us a client SDK, which is based on some generic client runtime. The cool thing about this is not bound up with AWS. You can actually write your own Smithy models for your own services, run it through the CodeGen, and then get your own SDK, which is pretty neat. So what we do for AWS-specific things, so originally, all that AWS-specific stuff that Nikki was mentioning, like regions, credential providers, and so on, that was all integrated. But now that we've separated that out, we have to bring it in separately. So we write a separate CodeGen on top of the language-specific one to provide those specific Amazon needs. And then we also depend on an AWS-specific client runtime, which in turn kind of depends on that generic one. So all of that AWS-specific stuff, we need it, but if you were going to make an SDK, you wouldn't need it.
All of the SDKs that we're talking about today share a couple of common features. Credentials providers, authentication mechanisms to connect to your AWS accounts and access your AWS resources. Retry policies so that you can configure when and how to retry a failed API call. And then various config tuning parameters like what region you're connecting to, HTTP timeouts for connecting to services, and even more specific things like endpoint resolvers for each service, or even swapping out the entire HTTP client engine under the hood that the SDK uses. All of these things are common configuration options that all three of our SDKs share, and newer SDKs will share in the future as well.
So let's start our deep dives. Rust is going to be the first one. So all this is happening in GitHub. You could go right now and check this out. If you have your phones, just snap a shot of the QR code and you can see our repo. So all of our repos are going to be divided into all of our SDKs are in two different repos. We have the one that holds all the Smithy stuff for generating the SDK. And then we have the SDK's repo itself. That's the one that we've linked here. So if you're familiar with Rust, using our SDKs is going to be really simple for you. You create a new project, and then in your cargo toml, you're going to have two common things anytime you use this. You're going to need to bring in AWS config. That has all this shared config stuff, kind of like the credential providers, retry config, things that we just mentioned. And then you're also going to want to use Tokio so that you can run this stuff asynchronously. And then lastly, for whatever services that you want to connect with, you're going to bring in that specific SDK. In this example, it's the AWS SDK for DynamoDB. So when making a request, again, we strove to make this very, very easy for people. You create a config. In this case, we load from end. So this is going to check your environment variables, whatever environment your thing's running in. Could be a Lambda. This could be checking your AWS profile. All that basically happens automatically in the same way that it would happen if you were using like the CLI. Once we've made that config, we pass that in when creating a new client. You would create a specific client for each service that you want to connect with. So in this case, it's the DynamoDB one that we imported earlier. And then all of the actions that you take with the service, we think of them as operations. So you say what operation you want to do. In this case, it's a scan operation. You'll use builder methods to set any inputs that you need to make that operation. In this case, we're saying that the table name is your table, and then we send it. And if you're familiar with Rust at this point, this will be a little simpler. You get a future. Futures do nothing unless you actually wait on them. So at this point, you have this big future with everything that needs to happen to do your scan, and so you just await it, and then that's it. So Rust has a couple of cool features. As I've been trying to emphasize, we made it as ergonomic as possible. So if you're used to Rust, you should already be used to this SDK. Everything is modular, as modular as we could make it. So you don't have to bring in S3 unless you want to talk to S3. You don't have to bring in EC2 unless you're talking to EC2. That minimizes compile times and binary sizes. We have native support for Tokio, as I mentioned earlier. It's pretty great to use. You can do all sorts of cool stuff with it. And we do our async logging with the tracing crate. We have a couple of different examples of how to do that. So if you're interested in how to set up that kind of logging for your own app, you can just go to the repo, look in the examples folder, and it's all in there. And you may have learned this from another talk that we had earlier in the week. Rust is native code, so it's energy efficient, and anyone using this SDK can benefit from that.
All right, next up we'll talk a little bit about the Kotlin SDK. So similar to what Zelda mentioned for the Rust SDK, we're hosted on GitHub. Our URL is pretty similar, and you can browse to us using that QR code if you like. Not only does all of our code and all of our commits go on here, but our roadmap is hosted on this repo as well. All of the issues that we're working on in real time are hosted here. And ongoing discussions that we have with users about maybe some design improvements or maybe some documentation that needs to be improved are hosted here as well. So this is the best way to engage with us if you're interested in getting more involved with the Kotlin SDK or with any of these SDKs, frankly. I guess also similar to Zelda, if you're familiar with Kotlin, you'll probably be familiar with Gradle and the Kotlin DSL for Gradle. We have just two requirements, two things you have to pull in to use an SDK. The first is the actual client that you want to use. So in this example, I'm showing using the DynamoDB client. And then we also need to pull in the Kotlin X coroutines library. Our library is built on top of coroutines, and so it needs coroutines to function. We'll go into a little bit more detail on that in just a second. Making a request is also pretty similar. It looks hopefully like what you'd expect from a Kotlin sort of library. The first thing we need to do is get a client. So we're instantiating using a DSL style builder, a DynamoDB client. And here we're explicitly passing in a region. The Kotlin SDK does have methods for being able to load from environment like Zelda showed, but this is just a more explicit version of that in case you're running in a situation where all your configuration isn't available in your environment. The very next thing we do is we use that client to call an operation, in this case list tables, and we can pass in as many parameters as we'd like to that operation afterwards. Limit here will just limit the number of results we get back. It's an optional parameter. We could just leave those braces empty if we didn't have any additional operations or any additional parameters to pass. The rest of the example shows doing something with the response. It shows getting the table names out, iterating over each one of them and printing them, and then finally closing the client to release any resources that are used by it. All right, so this shows an example of a relatively simple request. The response is small and finite, but the operations required for making a request with a streaming response are somewhat different. So again, this example shows getting a client, in this case the S3 client, and what we're going to want to call here is the get object operation. That's going to retrieve a binary from S3. The binary could be megabytes, gigabytes, it could be super huge. And so we're not going to get that response back all at once. Instead, the get object API call is going to take a second parameter aside from the request. It's going to take a lambda parameter where the response will be available. And everything that we need to do with that response should be handled inside that Lambda body or something that it calls, because once the Lambda body ends, the SDK will automatically release the response and free up any resources that are being used by that binary stream. And this helps make sure that we don't have any long-running memory leaks or that we're not using more resources than necessary. And again, we close the client at the end there to make sure that we're done using the client itself. All right, so our SDK also has a couple of special features. First off, we're built on top of a series of libraries called the AWS Common Runtime. The CRT provides us a base layer of functionality that can be reused by multiple SDKs so that we don't have to re-implement it every time. These are things like the basic I/O operations, HTTP, some serialization and deserialization, signing, credentials providers. All of these things are implemented down in the C layer and then bound to by Kotlin in a way that allows us to not have to reinvent the wheel here. In addition to that, as I kind of alluded to earlier, all of our calls in the Kotlin SDK are suspending. If you're familiar with Kotlin, if you're familiar with the suspend keyword, that's what we use to decorate every call that we make. And so that means that every API call you make has to be executed inside of a coroutine context. Run blocking is one of them that's shown at the top here. Async is another. But whatever it is, you need to kind of make an explicit decision about what threading model you want to use for each of these API calls. We thought that was the right thing to do because even for very simple operations where you'd expect the response to take milliseconds, those are still valuable milliseconds that you can be doing something else with your local compute resources. Whether it's making another API call, using a third-party library, doing some in-memory operations, there's no reason to necessarily just leave those blocking on a thread. So here's an example of invoking two different Lambda functions in parallel. One of them is called foo, one of them is called bar. And the results of what they return is not particularly important to the demo, but what it shows here is that we're executing them inside this async construct that's part of the Kotlin X coroutines library. That means they're going to execute in parallel, and then we're going to wait and collect them both in that printline method at the very end.
Swift. All right, let's talk about the Swift SDK for a second. Okay, so just like my fellow two colleagues here, it's also hosted on GitHub. I think one thing they didn't mention, though, that I think is important is that we talked earlier about the architecture of the SDK being split, especially so you guys can generate your own service clients in one of these languages, should you need it, from Smithy. Any of those repos can be found at github.com/AWSlabs/Smithy- fill in the language of your choice. Smithy Kotlin, Smithy Rust, or I think it's RS actually, Smithy Swift. I think we have Smithy TypeScript. We have a bunch of them now. So you can generate your own service clients from Smithy using that layer, and then this is essentially the layer on top where the SDK is generated and ours is just tagged through Swift Package Manager. So per Swift Package Manager, we wrote our manifest here in Swift, and as you can see, all we had to do was tell Swift Package Manager the URL that we would like to pull this package from, the version, and then inside the targets, we can indicate which products we would like to use. So just like these other SDKs, the Swift SDK is also modularized, so you do not need to pull in every single service. You can pull in just the services that you need. So in this case, we're actually just pulling in DynamoDB and from the Swift SDK, and then that's it, basically. That's all you have to do. If you want to do some kind of customization with the SDK, or you have to refer to something specific, we do have other libraries listed in our documentation, similar to like the core, the config library that they mentioned, but you don't actually need them if you're just going to do like a simple call. Making a request. Okay, so some context here in case if you have used the Swift SDK in alpha, because it has been in alpha for a couple months now. I think there is an important piece of context here if you're familiar with Swift. Swift concurrency just dropped fairly recently in Swift 5.5, but before Swift concurrency dropped, unfortunately, all we had was completion handlers. So right now, the SDK does have two sets of APIs, completion handlers and the await signatures. However, the completion handlers will be going away, which is why I'm only showing you the await syntax here. So in this example, we instantiate a client with a region. Because config isn't explicitly defined here, it means that you're basically just taking all the defaults and I'm creating the config object for you. It's just like a nice thing that I'm doing. If you need to create the config object because you need to pass in specific overrides, you absolutely can do that. And then I'm creating some data and then calling put object. So this is actually an example of a streaming request, except in this example, I already have the stream of data. So I'm just turning it into a byte stream, calling the bucket and the key, and then I'm awaiting s3 client.put object, and then I can just return the response, which, I don't know, in this case, probably just has like success or data in it if it went through. Special features. Okay, so similar to the other SDKs, I don't have an amazing slide to list them all, but we do have integration with Swift Log. We have integration with Swift Collections. So these are two packages put out by Apple that eventually, hopefully, will make their way either into the standard library or standalone packages that almost every Swift user uses. Obviously, the Swift SDK is extremely idiomatic to Swift, and we followed conventions everywhere. And then this point actually I think is really an important point. The entire Swift SDK is built on the CRT, not just pieces of it. And I think the power in that actually is that the Swift SDK can run anywhere. So it can run on Linux, it can run on Mac, it can run on iOS, and then we have other platforms coming soon like tvOS, watchOS, Windows. Yes, we are going to add Windows. You know, we can run anywhere you like. So there is a Swift CRT bindings library that we just basically call native C from. It doesn't actually affect performance or the binary size, so everything is just the same because Swift C interop is just seamless. So yeah, we are built on top of the CRT.
So earlier we teased that we built something together. This is an architecture diagram of what we built. So what's going to happen is everyone's going to start sending texts, and we're going to use Twilio to receive all those, and those are going to get sent to a Rust-based Lambda. That Lambda is going to read your text and the images that you send along with it, make a little meme, put it in S3, and then do a couple of other little things. Then notify our Kotlin backend that there's a new image.
The Kotlin backend is going to pick that up. It's going to inspect the image and then save some metadata to a DynamoDB table. It's going to mark the image as unmoderated, meaning it needs a human to take a look at it and see whether it's good to show or not good to show. And then that's one thing that the Kotlin backend will do. The other thing that it will do is it will listen for requests from a front-end app to show the approved memes. So it's kind of running as a Ktor web server in a Fargate container.
And we have two front ends. The first front end is just calling the Kotlin backend, similar to you would find a normal iOS application. The second one is doing something a little bit unique to demonstrate the Swift SDK. It's actually communicating directly with the DynamoDB table to moderate your images, make sure we're not displaying anything inappropriate.
Cool. So the instructions are, I hope, pretty simple. I would love for all of you to take out your phones and either snap an image right now, hopefully ping or JPEG, send text in the same message as that image. Text should be 2 sentences. Any text before the first period will go at the top of the image once we do our generation, and text after that first period will end up on the bottom. If you want, you can just send 1 sentence. You don't have to send 2. You could even start your sentence with a period, and then it would just put stuff on the bottom. We have a little example of so if you send this image in with that text, that meme will be generated. And that's all.
So, send your images in with your text. We'll leave that up there for 1 second, and then we'll pull up the feed to see how many memes we're getting.
All right. Are you ready? Are they coming in?
I haven't seen one yet. I'm waiting. Maybe they're still being generated.
Could be. Oh man, I hope someone sent something in. Raise your hand if you sent something in. Okay, we got a couple. Oh yeah, I can see them. So right now, they're all going to the moderation app, as we said. Nikki has that open on her phone, and so she's approving or denying them. Now you can see they're starting to pop up.
I don't know about the Wi-Fi in here. Come on. Downloading images is hard.
Yeah, I should have added a compression step, I guess.
That's okay.
Is there a limit to the image size?
No. Please don't DDoS me.
No, I just want to picture. I don't know what resolution and sense it.
Yeah. For that, luckily the meme generation is resolution independent, so it'll just size the text accordingly. But it will be a giant image that takes a long time.
We did test it with some large images, although not in this room specifically.
Right. Key fact. Different network conditions. I'm pulling in some more right now. Hold on.
While we're waiting for these to load, does anyone have any questions? Yes?
Yeah, so you mentioned that the SDKs are updated daily at roughly 11 a.m. Is there a way to see what's new?
So the question is there a way to see what's new when SDKs are generated every day at approximately 11? Yes, most of the SDKs publish what's new notes along with every release. Some package managers include those as part of the packages. Others, I think, do not, and you may have to go to the SDK page on the Amazon website. But yes, every SDK has the capability to display those what's new notes. They just may do something slightly different with it. But you would see things in there like there's a new feature for the SDK itself, some new credential provider or some new retry policy or something, or there's a new AWS service or a new AWS feature for a service. All of those should be available in release notes.
Yeah, I know on the Rust team, we write change logs that are in Git. So if you went to Git, you could also see the notes there. We know, bugs that we fix, things like that.
One more follow-up question is, do you have the code base for this what
Yes. All of the code that we wrote is in one repo, and we have the QR link for it at the end. So you can see the Rust Lambda, the Kotlin backend, and the Swift front ends.
So, which is the involvement of the product teams in the creation of the SDKs? Like, I know when we release a couple new features, but they talk to you and you code the SDK for that, they code that part, or what's the collaboration with them?
Yes, the question is like, what's the sequence of operations? What's the ownership when a team like DynamoDB releases a new feature? That's a great question. When Zelda was showing the slide on Smithy, what that is a modeling language that allows teams to describe their APIs in a concise, kind of repeatable format. That modeling language is what the service teams communicate to the SDK team. There's a little bit of work under the hood to review those changes and to approve them or deny them or improve them based on certain like feedback criteria. But once they're accepted, then we don't handwrite much of anything for that change. In fact, in 99% of cases, it just automatically gets code generated into our SDKs and gets built and released. There are rare situations where there are some features that are so specialized or can't be captured adequately with the modeling language where there is some hand-rolled code, but that's more and more of a legacy thing, and going forward, more and more teams are using the Smithy modeling language to accurately describe their APIs to us.
Oh, yeah, follow on. Okay, yeah, that stuff is really interesting. If anyone is good at reading Kotlin and is interested in code generation, definitely go look in our repos for how we did the customizations, because if you wanted to use Smithy to do your own API, you might also have to create a customization if you have some very special behavior that you want to enable. It's not too hard. I mean, I've never done Kotlin before. I joined the team, but I joined a couple months ago now, and I've been able to write them. And they're really cool, honestly. Code generation is just so neat.
Yeah.
Thanks again for bringing me this SDKs to all these languages. Historically, it felt like the Java SDK was the golden SDK, and then the other SDKs were all playing catch up. One example of this was the anonymous AWS Credentials provider, which is provided in the Java SDK for, say, anonymous S3 bucket requests, which is not, say, in the Node.js SDK even now. Going forward, how is that changing, and do you see things like anonymous AWS credential provider in these SDKs?
Anonymous credential providers? What do you mean by that? Like, you can provide your own credential provider?
No, you're providing no credentials for unauthenticated requests.
Okay.
Publicly accessible S3 buckets, for example, if you wanted to get an object from a public bucket, you could use that without providing any.
Got it. So in Smithy, that's actually designated through a property on top of the model. So the service teams, they write their own models, right? And then they get generated through our generators. So we actually detect whether or not there's an auth property in Smithy. And then if that operation doesn't have it, we will not require authentication.
Maybe addressing somewhat of your larger point, you're right that the Java SDK is one of our oldest and best supported SDKs at this point. It also sees a lot of use, quite frankly, just because of how many different platforms it can run on. And until this dev preview, if you were writing Kotlin, you were probably using the Java SDK. If you were writing Scala, you were using the Java SDK. There's a lot of people coming to the Java SDK for their features. But we do recognize that feature parity is kind of uneven across the SDKs. The CRT slide that I showed there a while ago is one of the efforts to address that, to implement that base level functionality one time, and then to get the SDKs to consume it in a reliable manner, to bind to it on their platform in a way that makes sense. We're not there yet. We're not in the perfect situation, but that's one of our plans to address that.
So for example, like S3 performance, like, we've done a lot to improve the performance of S3 downloads and uploads for our older SDKs like Java. Well, the CRT now has that basically built into their runtime so that we can take advantage of it on day one.
Yeah. I'm sorry, can you repeat the question a little bit louder? So I think the question is, is the CloudFormation team using our SDKs under the hood, or are they using something else? That's a great question. I don't know. I don't know the answer to that. They certainly could, and there are a lot of internal users, even within AWS, of the AWS SDKs. It's one of our preferred methods, because the alternatives are calling through HTTP methods directly, which it's doable in any language, but it's messy and it's not fun. Or doing some sort of more direct invocation of another team's resources. So I can't say with confidence that they're using the SDKs, but I think it's likely.
One thing that I know other teams are using, at least for Rust, is other teams are using Smithy to generate their own internal services that aren't public, and that's already happening.
Yes?
Is there a public roadmap for moving the legacy SDKs to Smithy?
The question is there a public roadmap for moving the other SDKs to Smithy? Zelda, Nikki?
I don't believe so. It's definitely in our plans and roadmap, and it's actually currently happening. So the other languages have either moved over, like TypeScript, I believe Go also, but some of the other languages that are a little bit older, like Java or .NET, they're actually in process of writing their Smithy generators. There's not a public roadmap for it, but I can tell you, it is happening.
Yes?
Are you using formal methods or any other particular testing strategy to test all of these generated code?
I heard something about testing strategy. Can you repeat the rest of the question?
Yes. So the question is whether you are using formal methods or any particular testing strategy to make sure that all of this transpiling and compilation, stuff like that, work in the different languages.
Yeah, so we have a couple of different testing strategies to address the wide variety of things we have to support. The Smithy team itself provides protocol tests for each of the different protocols that are used by AWS services. All the AWS services fit into one of, I think, 6 or 7 different protocols. And so we can test each of those protocols independent of a service and have a high degree of confidence that any calls to a service that uses said protocol will work. Beyond that, for all the customizations we do, we also write tests for those. So if we're bypassing the code gen for some reason and we're hand rolling our own implementation of some particular operation, you can be sure that will get tested as well. There's additional testing strategies, like many of our documentation writers maintain repositories of example code that runs on these SDKs and calls real operations on real accounts. Every time we release a new SDK or every other time, there's a cadence to it. They rerun those tests and verify that everything is still working.
In Rust, we have a lot of tests. And again, this is all open source, so you could actually go and see the tests that we're running to verify these things. And on top of this, with Rust will actually, when it sees example code and documentation, it will make sure that it compiles and it can even run it. We tell it not to run it for anything that actually would call a real service and affect something. It's not idempotent. But we can have a really high degree of confidence that all the examples that we're putting out are real code that you could copy paste into your project and then it would just work.
All right, so the internet finally caught up with us while we were asking questions, so I've been sitting here approving images, but we did get some memes, and some of them are actually pretty funny.
Yeah, these are great, you guys.
Good job, guys.
Did someone eat a bear? Is that what that was?
That was a bear, yeah. Rust is fast when your await returns.
It's true.
All right, any more questions?
This is
Okay.
good.
You guys have some good memes. I think that's the end. Yeah. Sorry about the internet.
Yeah.
Question, mostly for the main language, Swift and Rust. Have you noticed any platform differences when running on, say, Linux versus Mac OS? Because in my own personal experience with Swift, I've noticed a few differences, like using the SQLite library, I ran into some issues on Linux that I did not run into in Mac OS. I'm curious if, as SDK teams, you've seen any of those platform differences and how do they manifest?
I mean, I have, yes. I've accounted for them in the SDK, though, so that the same code runs and gets the same output on both platforms. But yes, I have encountered them. I've encountered slight language differences even, like writing something slightly differently in Swift will work on one platform and not on the other. And then also just like a really important one that I'm actually trying to fix right now is OpenSSL. So on Linux, you need to have that installed as a dependency if you're going to use Swift on Linux. I'm trying to work on that to bundle it in so you don't have to have it pre-installed, but right now that is a hard dependency of using the Swift SDK on Linux. On Mac, obviously, we have built-in libraries so you don't have to install anything.
And yeah, Rust is very much the same, actually. The biggest place where people are going to run into these differences is with SSL. We currently support Rust TLS, so that's a bundled one. So that actually is very, very portable. However, it does increase binary sizes, and so we're working on supporting other things like native TLS, stuff like that.
Yeah, in progress, basically. In my ideal world, you run it on Linux and Mac, and you do the same thing, and you don't have to worry about anything. But in progress.
Any more questions? The question is, do we have a mocking framework for the SDK? Kotlin does not have a mocking framework yet.
What do you mean, like you want to write SDK calls for unit testing the SDK itself?
Unit testing my code that is using the SDK.
I can speak at least for the Rust SDK. We don't have mocks for Rust specifically, especially because mocks in Rust are not quite a common pattern. But we do have a lot of ways of testing things, like especially when you want to make sure that you are forming good requests and things like that. We have all sorts of ways of switching out different layers of the network stack to achieve different behaviors, and this is how we test things like retries and timeouts. We even have the ability to record and replay like things that happen in a connection. So you could have like a known good interaction and then write tests that kind of replay that back to ensure that you're getting the same behavior.
We also don't have a mocking framework, but you could do very similar things that she mentioned with the Swift SDK. Generally speaking, you could also write tests in Smithy actually and generate tests from there. But you know, you also have to have your resources stood up somehow. So if you're testing against actual resources being alive in your cloud account.
I will also say the Kotlin SDK uses builder objects to create its parameters for passing to APIs and for getting responses back from APIs. Those are publicly available, publicly usable by any consuming code. So you could use those in your unit tests if you want, although it may not be the most ergonomic or it may not adapt to your testing situation the best. If you find that's the case for any of our SDKs, that there are features you want, things like testing, things like additional configurability, we highly encourage you to come to our repos, drop us a note, explain your use case, and we'll engage with you and try to figure out what it is that you're looking for. And then try to use community upvotes to gauge how popular this feature is so that we can slot it on our roadmap in an appropriate place.
Yeah.
If you want it, there's a likelihood that someone else wants it too. It just needs to be articulated so that we can get it in our roadmap. We have a lot of things to do, and we don't have all the time in the world to do them, so you guys can help us decide which order those happen in.
Yeah, it's really important to us that we implement the things that you want. I mean, we're doing this all for you, So if you spend the time to let us know like how we can make your day easier, file us a nice issue, and we would be so happy.
Yeah, issues. We also have discussions on GitHub open, at least in my repo, so you can open a discussion if you want to talk about a feature or a special request or something like that. And then our roadmap is also public as well on GitHub, so you can know what we're up to. We can also go back to those GitHub URLs if you didn't snap it the first time, if you need them again. But if we just go to our next slide, this is just our demo code at this link.
All right, well, if there's nothing else then, please fill out the session survey that you guys have. That'll really help us give the session better every time.
We got a lot more memes actually too, if we want to go back to that.
We can just show memes for the rest of the time here.